There is currently no national electrical code requirement mandating a grounding mat at every electrical service, commercial installation, or residential location. An electrician mentioning such a requirement might be mistaken or have possibly misunderstood the code provisions. It is, however, plausible that they were referring to a static mat. Static mats are specifically used in the computer and electronics industry to prevent electrostatic discharge, often abbreviated as ESD. Electrostatic discharge is the sudden flow of electricity between two electrically charged objects caused by contact, an electrical short, or dielectric breakdown. It's a common phenomenon and can be observed when touching a doorknob after walking across a carpet on a dry day. While generally harmless to humans in everyday situations, ESD can be extremely damaging to sensitive electronic components. In the context of electrical installations, grounding and static control are two distinct concepts. Grounding, as defined by the National Electrical Code, is the connection of electrical equipment and systems to the earth, establishing a low impedance path for fault current to return to the source. This grounding system plays a crucial role in safety by minimizing the risk of electrical shock and facilitating the operation of recurrent protective devices, such as circuit breakers and fuses, during a fault condition. A proper grounding system typically involves a grounding electrode, such as a ground rod, ground plate, or the metal water pipe connected to the service equipment. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the ungrounded service conductors. Furthermore, equipment grounding conductors, which are typically green or bare, connect the non-current carrying metal parts of electrical equipment to the grounding system. These conductors provide a path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. The NEC outlines specific requirements for grounding different types of systems, including alternating current systems in Article 250. These requirements cover topics such as grounding electrode systems, grounding conductors, and equipment grounding. Static control, on the other hand, focuses on preventing the buildup of static electricity and safely dissipating it to prevent damage to sensitive electronic components. Static mats, wrist straps, and other static controlled devices are commonly used in environments where electronic components are handled or manufactured, such as computer repair shops, electronics assembly plants, and data centers. Static mats are typically made of a conductive or dissipative material that allows static electricity to flow slowly and safely to ground. When a person stands on a static mat or wears a wrist strap connected to the mat, any static charge that has accumulated on the body is safely discharged, preventing it from damaging sensitive electronic components. The effectiveness of a static mat depends on its material properties, size, and grounding connection. It's important to ensure that the mat is properly grounded to a known ground point, such as a grounded electrical outlet or dedicated grounding rod. The resistance between the mat and ground should be within a specific range, typically between 1 megohms and 10 megohms, to provide adequate static dissipation without creating a shock hazard. The NEC does not specifically address the use of static mats, as they are not considered part of the electrical grounding system. However, the code does address the general principles of electrical safety and the need to protect equipment from damage. While static mats are not required by the NEC for general electrical installations, they may be necessary in certain environments where sensitive electronic components are present. For example, a data center may use static mats to protect servers and other electronic equipment from ESD. Similarly, a manufacturing facility that produces electronic components may require employees to wear wrist straps and work on static mats to prevent damage to the products. In summary, while there is no NEC requirement for grounding mats at every service, commercial, or residential location, static mats are used in the computer and electronics industry to prevent electrostatic discharge. Grounding and static control are distinct concepts, with grounding focusing on electrical safety and static control focusing on protecting sensitive electronic components. The NEC provides specific requirements for grounding electrical systems but does not specifically address static mats. However, static mats may be necessary in certain environments where sensitive electronic components are present. When dealing with electrical installations, it's important to consult the latest edition of the National Electrical Code and other applicable standards to ensure compliance and safety. Always consult with a qualified electrician or electrical engineer for specific guidance on grounding and static control requirements. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is widely adopted by state and local jurisdictions and serves as the basis for electrical safety inspections. The purpose of the NEC is to protect people and property from electrical hazards. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a design manual, but it provides minimum requirements for electrical installations. Electrical engineers and electricians use the NEC as a guide to design and install safe and reliable electrical systems. The NEC is divided into chapters, articles, and sections. Chapters cover broad topics, such as general requirements, wiring and protection, and equipment for general use. Articles cover specific topics within each chapter, such as grounding and bonding, overcurrent protection, and wiring methods. Sections provide detailed requirements for each topic, such as the size of grounding conductors, the rating of circuit breakers, and the type of wiring allowed in different locations. The NEC also includes tables and examples to help clarify the requirements. These tables provide information such as the ampacity of conductors, the size of conduits, and the grounding electrode conductor size. The examples illustrate how to apply the NEC requirements in different situations. It is important to note that the NEC is a minimum standard, and additional requirements may be necessary to meet specific project needs or local codes. For example, some jurisdictions may require more stringent grounding requirements or may have specific rules for wiring in hazardous locations. When working on electrical installations, it is essential to consult the latest edition of the NEC and any applicable local codes. It is also important to have a thorough understanding of electrical theory and safe work practices. Only qualified electricians should perform electrical work. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. It is important to be aware of these standards and regulations and to comply with them as applicable. Electrical safety is paramount. Always follow safe work practices and use appropriate personal protective equipment when working on electrical systems. Never work on energized equipment unless it is absolutely necessary, and always de-energize and lock out the circuit before working on it. If you are not qualified to perform electrical work, hire a licensed electrician. The National Electrical Code addresses grounding in Article 250. This article provides comprehensive requirements for grounding electrical systems to ensure safety and minimize the risk of electrical shock. The primary purpose of grounding is to create a low-impedance path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers and fuses to quickly trip and energize the circuit in the event of a fault. This prevents dangerous voltage buildup on metal equipment enclosures and reduces the likelihood of electric shock. Article 250 covers various aspects of grounding, including grounding electrode systems, grounding conductors, equipment grounding conductors, and bonding. The grounding electrode system provides a connection to the earth, typically using a ground rod, ground plate, or metal water pipe. The grounding electrode conductor connects the grounding electrode to the service equipment, such as the main panel. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the ungrounded service conductors. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system. These conductors provide a path for fault current to flow back to the source, tripping the overcurrent protective device. Bonding is the process of connecting together all metal parts that are likely to become energized, creating an electrically conductive path. This ensures that all metal parts are at the same potential, reducing the risk of electric shock. Article 250 also addresses grounding requirements for specific types of systems, such as separately derived systems, which are systems that receive power from a source other than the main utility service. These systems require their own grounding electrode system and bonding connections. The NEC also provides specific requirements for grounding in different types of locations, such as hazardous locations where flammable materials may be present. In these locations, special grounding techniques are required to prevent the buildup of static electricity and reduce the risk of explosion. Proper grounding is essential for electrical safety. It is important to follow the requirements of the NEC and other applicable standards when designing and installing electrical systems. Always consult with a qualified electrician or electrical engineer for specific guidance on grounding requirements. Some common misconceptions about grounding include the belief that grounding protects equipment from lightning strikes. While grounding can help to reduce the risk of damage from lightning, it is not a substitute for a lightning protection system. Lightning protection systems are designed to intercept lightning strikes and safely conduct the current to ground, protecting the building and its contents from damage. Another misconception is that grounding is only necessary for large electrical systems. In fact, grounding is important for all electrical systems, regardless of size. Even small appliances and electronic devices should be properly grounded to prevent electric shock. It is also important to understand the difference between grounding and bonding. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same potential. Both grounding and bonding are necessary for electrical safety. When working on electrical systems, it is important to use proper grounding techniques. Always use approved grounding connectors and conductors. Ensure that all grounding connections are tight and corrosion-free. Never remove or bypass grounding conductors. If you are unsure about any aspect of grounding, consult with a qualified electrician. Static electricity is an electrical charge that builds up on the surface of an object. It is caused by the transfer of electrons between objects, typically through friction. When two objects made of different materials are rubbed together, electrons can be transferred from one object to the other. The object that gains electrons becomes negatively charged, while the object that loses electrons becomes positively charged. Static electricity is more common in dry environments, as moisture in the air can help to dissipate the charge. Static electricity can cause a variety of problems, including shocks, sparks, and damage to electronic equipment. When a charged object comes into contact with another object, the static charge can discharge, creating a shock or spark. This discharge can be harmful to electronic equipment, as it can damage sensitive components. To prevent static electricity, it is important to control the environment and use static control devices. This includes maintaining a proper humidity level, using static dissipative materials, and wearing static control clothing. Static dissipative materials are materials that allow static electricity to flow slowly and safely to ground. These materials are often used in flooring, work surfaces, and packaging. Static control clothing, such as wrist straps and grounding mats, provides a path for static electricity to discharge from the body. In addition to these measures, it is important to handle electronic components carefully. Avoid touching sensitive components directly, and always use grounded tools and equipment. When transporting electronic components, use static shielding bags to protect them from static electricity. Static electricity is a common problem in many industries, including electronics manufacturing, healthcare, and printing. By taking appropriate measures to control static electricity, it is possible to prevent damage to equipment and ensure a safe working environment. The human body is a good conductor of electricity and can easily accumulate static charge. When a person walks across a carpet or touches a doorknob, they can generate a static charge of several thousand volts. This charge can be harmful to sensitive electronic components, as it can cause damage or malfunction. To prevent static electricity from damaging electronic components, it is important to use static control devices. Wrist straps are commonly used to ground the body and prevent static charge from building up. These straps are typically worn on the wrist and connected to a grounded object, such as a workbench or grounding mat. Grounding mats are placed on work surfaces to provide a static dissipative surface. When a person stands on a grounding mat or touches it with the wrist strap, any static charge on their body is safely discharged to ground. Static control clothing, such as lab coats and gloves, can also help to prevent static electricity from building up. These garments are typically made of static dissipative materials that allow static charge to flow slowly and safely to ground. In addition to these devices, it is important to control the environment to prevent static electricity. This includes maintaining a proper humidity level and avoiding the use of materials that generate static charge, such as plastic and synthetic fabrics. By taking these measures, it is possible to prevent static electricity from damaging electronic components and ensure a safe working environment. When working with sensitive electronic components, it is important to follow proper handling procedures. Always handle components by their edges and avoid touching the pins or leads. Use grounded tools and equipment, and wear a wrist strap or grounding mat. When transporting components, use static shielding bags to protect them from static electricity. By following these procedures, it is possible to minimize the risk of damage from static electricity and ensure the reliability of electronic equipment. Electrical codes and standards are developed by various organizations, including the National Fire Protection Association, the Institute of Electrical and Electronics Engineers, and the American National Standards Institute. These organizations bring together experts from different fields to develop consensus-based standards that promote electrical safety and reliability. The National Fire Protection Association, or NFPA, publishes the National Electrical Code, which is the most widely adopted electrical code in the United States. The NEC is updated every 3 years to reflect changes in technology and best practices. The Institute of Electrical and Electronics Engineers, or IEE, develops standards for electrical power systems, including grounding, protection, and control. These standards are used by engineers and designers to ensure the safety and reliability of electrical power systems. The American National Standards Institute, or ANSI, is a non-profit organization that coordinates the development of voluntary consensus standards in the United States. ANSI does not develop standards itself, but it accredits organizations that do. ANSI-accredited standards are used in a wide range of industries, including electrical, mechanical, and civil engineering. Electrical codes and standards are constantly evolving to keep pace with changes in technology and best practices. It is important to stay up to date on the latest codes and standards to ensure that electrical installations are safe and compliant. The NEC is not a static document, but is constantly being revised and updated to reflect changes in technology and best practices. The NEC is developed through a consensus-based process that involves experts from different fields, including electricians, engineers, manufacturers, and regulators. The NEC is divided into chapters, articles, and sections. Each section contains specific requirements for electrical installations. The NEC also includes tables and examples to help clarify the requirements. It is important to consult the latest edition of the NEC and any applicable local codes when designing and installing electrical systems. The NEC is not a design manual, but it provides minimum requirements for electrical installations. Electrical engineers and electricians use the NEC as a guide to design and install safe and reliable electrical systems. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers and the American National Standards Institute. It is important to be aware of these standards and regulations and to comply with them as applicable. The NEC is a complex and comprehensive document, but it is essential for ensuring electrical safety. By following the requirements of the NEC, it is possible to protect people and property from electrical hazards.